Okay, good morning everybody. I hope everyone's having a wonderful day. So today I'm going to be talking about some more lower bound results, and then I'm going to be moving into another topic called amortized analysis. So this is kind of what I would consider one of these, like if you're thinking about lower bounds, this is kind of like one of the most standard ones that if you're going to run into one of these results, this is one that is a very good one to know about, especially at least if you're thinking about different algorithms for sorting, for many reasons. So we're going to be talking about, for this part, about comparison-based sorting algorithms and lower bounds we can establish. Last day, I talked about how we can establish lower bounds using reductions. So I showed you a very simple way to show that that big omega of n is the least amount of operations you're going to need to solve any sorting problem instance, right? In the worst case. So that bound, like, once you realize that, because what I did was I used computing the maximum to help me prove that result. Now here, what I'm going to do is I'm going to do something a little different. So I've shown you a few different ways. We've done adversarial arguments, I've done this reduction approach, and then now I'm going to show you how we can use a model to measure complexity of any algorithm for a given problem under certain key assumptions. So we're going to measure complexity based on a model that we're going to conceive. So this model should hopefully fit everything we can think of when we think about an algorithm that solves that problem. At least that's what we would like. So we want to keep our models general and with as few assumptions as possible so we can make nice general results about lower bounds. I'll come back to that in a moment after we finish talking about this particular result. So we're going to focus on comparison-based sorting. Now, you might ask, Dan, what the heck is a comparison-based sorting? Now, almost every sorting algorithm you've encountered, if not, it might even be every algorithm you've encountered for sorting at this point, is a comparison-based sorting algorithm. Bubble sort is, insertion sort, you may know several others of quadratic running times. You may know other ones like merge sort, quick sort, heap sort possibly. These are all comparison-based sorting algorithms. Now, what we're going to do is we're going to kind of fit all of these kinds of algorithms, the ones that make comparisons between two elements and they do something. So we're going to measure the complexity of one of these comparison-based sorting algorithms. Not any one given one of those, just only one of them. I'm talking about any comparison-based sorting algorithm by measuring it using this so-called comparison-based model. So here's what I'm going to do. I'm going to assume I'm given an array of n distinct elements. Now it's worth noting that I don't need that distinct part. The arguments I use will generalize so I can have inequalities like less than or equals. But I'm just going to assume that the elements can be listed so that like x is less than y or y is less than x. So that it makes it easier for me to tell you like, oh yeah, this one is less than that one. But I must stress that isn't necessarily needed for all the arguments. There's ways to generalize these arguments further. But it makes it easier for our discussion, and it also makes it easier for proving the bound. So, and also it's worth noting, of course, when they're all distinct anyways, those are all instances of the sorting problem, right? So, I'm just going to assume that you're given some array array L of n distinct elements. I'm getting ahead of myself. And I'm going to make no assumptions about what these elements are other than that they're comparable. That means I can tell you this or this. So, like I said, it's going to be very general. Now, the word comparison in this comes from the idea that I can form a comparison. Now, I don't know exactly what's going to come as a result of the comparison, but this comparison has to happen. So, I'm going to consider any two elements in L, and I'm going to say that a comparison happens if this kind of query happens. So if xi is less than xj for two elements xi and xj. So I'll say that this is a comparison. And the answer from a comparison is either yes or no. So kind of like when we talk about adversarial arguments, remember I told you, oh yeah, no, that the algorithm will ask questions about the input, right? This is going to be very similar to this. But every time I do this, this counts as one comparison. So the trick here is that we're going to be very lenient about what the algorithm does with this information. So we're going to say that the algorithm can reorder elements and there is no cost of a comparison when this happens. So it could permute around elements, but anytime it does one of these comparisons, anything that looks like this, that counts as one comparison. Are we clear about that? So just the difference between what a comparison means and what everything else is just, I'm allowed to shuffle around the elements that I get for free. I'm just only counting the comparisons. Hence why I'm calling this a comparison-based model. But the idea is that the algorithm must output a permutation of the input. So what do I mean? If I give you an array L, it must be that it gives me an ordering of the elements in that array in sorted order. So that's its job. So it's just going to give me back an assorted array. Now, I must stress that any of the comparison-based algorithms you've seen or possibly learned, so just a few I want to point out just for our interest, merge sort, quick sort. I mentioned some variants of quick sort that will be the ones that may be of interest in relation to this, and you may have seen heap sort. So these are ones of particular interest because we know that there's ways to take these algorithms and make them run in Big Theta and log n. There's ways to do it. So I want you to keep that in mind when I'm trying to come up with our lower bound. Because remember, this lower bound, this big omega n, that's not a very good lower bound, right? I could have told you that because I have to look at each element at least once, right? I want something a little stronger. So something I could tell me more about the sorting problem. So we're going to adopt this model to see if I can do any better. But remember, this model only applies to algorithms that fit these rules. Is that clear, everybody? Give me a thumbs up if it's clear. Okay, I think we're good. So if it does not fit this model, then this result is not going to necessarily apply. One other technical remark I want to point out is that the result I'm going to show you here today technically applies to any deterministic comparison-based sorting algorithm. However, there are ways to generalize it, so we could be talking about randomized comparison-based sorting algorithms. But the argument isn't exactly the same. It's quite similar, though. So deterministic meaning that every time I run the input, it does the same sequence of operations every single time for a given input. So if I give you a different input, it might do something else. But the point is that for one input, it doesn't have any randomized behavior that's happening. So that's at least the context for which I'm using this term. Okay. So it's also worth, I'll mention this later, but I'm going to be obviously working on worst case analysis here. But it's also worth noting that the result we're going to establish also applies for average case. So now you might ask, Dan, how does this all stick together? So what I'm going to do is I'm going to use this idea of a decision tree. Now this is what the model gets described using as a decision tree. So we're going to have internal nodes that are going to represent our queries or comparisons. So whenever I do a comparison, that comparison is going to be represented by an internal node in the tree. So remember, internal nodes, those are ones that have at least one child in a tree versus external or leaf nodes. These are ones that have no children in the tree. So leaf nodes are going to be, the labels of these are going to be the output. So I thought I would give you an example of what I mean by this. So I'm going to show you an example here where I'm going to try sorting 3 elements, x1, x2, and x3. So this would be, of course, an array of length 3. Now, I must stress, this is something I must stress, is that every one of those comparison-based sorting algorithms has a different decision tree possibly. So I give you a sorting algorithm, it's going to have another decision tree possibly. But I want to just walk you through this idea, just so we get the idea and what we can get some intuition around this. Because remember, when I run the sorting algorithm, it will take the elements and possibly change them around. It'll do these comparisons and it'll produce some output, right? So I want to show you kind of the parallel between that and this. So imagine I have 3 elements. Now suppose somewhere in this process, I ask, is x1 less than x2? There's either 2 possibilities, either yes or no. If it's yes, then I proceed to ask about x2 and x3, possibly. And saying here I have x2 is less than x3, there's two possibilities, either yes or no, because remember all the elements are distinct. Now, if I have two yes answers, I can actually conclude the ordering for which, like the way I should permute all these elements such that they're sorted. So if I say yes twice, notice it says x1 is less than x2, then we know x1 is less than x2. But if I say x2 is less than x3, okay, so that means if I say yes, then I know right away that x1 is less than x2 is less than x3. So this is in fact the ordering that will give me the array sorted. Is everybody okay with that so far? However, I must stress that if you get a no, you might have to ask more questions to figure out if you have the array in sorted order. So, like I said, so I must stress that each sorting algorithm has its own decision tree. Now, I have a question for you. I want you to think about this for one moment. Okay. I want you to look at where I'm directing from the root down to a leaf. What would be a representation of an execution of the algorithm that would correspond to this decision tree? So what does, say for example, if I start up here at the root and I reach one of these leaf nodes, what does that represent? Can somebody tell me? I want you to think back to what I just said before about, oh, well, when we run a sorting algorithm, perform some comparisons, and then it does stuff, right? But what does this represent? What is I don't want to use the P word yet, but what does that represent? What does this represent if I go from up here and say I zigzag down this way and I get to right here? What does that represent? So this is the connection between our model and what we think about when we do our typical analysis. A permutation where all the elements are sorted. Yes, that's the output that you get when you get down to one of these leaf nodes, but it is in fact the way the algorithm processes all the comparisons, right? So one path of this is actually the execution of the algorithm, and it's actually listing out the comparisons for you. So a path is an execution of the sorting algorithm. Does everybody see that? So if I follow one of these paths, it's just telling me what comparisons are done in what order, and when it finishes, it returns a sorted array, right? Which is one of these leaves, right? So does everybody see the parallel? So in our comparison-based model, this decision tree, the path represents an execution of the sorting algorithm, and we have this nice parallel between the two. So if you want to ask me, Dan, what does this whole tree represent then? Let me just say something about that. So I just want to remark that the decision tree contains all sequences of decisions, for the sorting algorithm. So it's just telling me the comparisons, the order in which the comparisons are happening. And remember, for each one of your sorting algorithms, I want you just to imagine this. You can think about it more after lecture. I encourage you to do this. Just remember, you just need the intuition of it. It's just that, for example, when I do bubble sort, right? Like I have to compare two elements, right? So like I compare this one and that one, and I do a swap, right? Well, each one of those comparisons is representing one of these nodes here in my tree. So each one of these sorting algorithms will have some order it's going to do this for any one given instance, right? So each one of these is going to correspond to some execution on this tree. So I have a question for you. If I wanted to determine the worst case scenario, like we would before with any one algorithm, so just with one algorithm, what would that correspond to in this tree? Somebody suggested choose no every time. Now remember, it depends on the input to your problem, right? Sorry, the input to the algorithm. Now, if I answer no every time, indeed, there's going to be some path that's going to get me down over there. But there's a much more general way to talk about this. Anything on the very bottom row, and the longest, that's exactly it. So notice that in the worst case is actually going to correspond to the longest path in this decision tree. Why? Because now I must stress, remember, each sorting algorithm will have its own decision tree. That's the big kind of observation. Now, I want you to think about this. So I'm going to say the longest path in the tree corresponds to the number of comparisons required in the worst case. So like I said, like everybody seemed to got the idea of, is that if I find the longest path in this tree, that'll tell me how long it can take in the worst case. So the idea is that, and so this is just to give you a general game plan of what we're going to do. So I'm going to try to find a relationship between this longest path in a decision, any one decision tree, and argue to that actually, I'll come back to one point in this, but what this relationship this tree has with the longest path in relation to its leaves. And these two things come together in a way that I can actually bound the length of the longest path. Can somebody tell me what is the length of the longest path, like in terms of trees? Like what do we call that? What do we call that? So it starts with an H. And the height, it's the height. It's the height, exactly. So it's the height of this tree. That's the length of the longest path. So we're going to try to, and it must be stressed that, like it's being pointed out in the comments, it is possible that there can be multiple longest paths. So like that means that they're both going to have they're both going to reach the same level of this tree. Just like in my example here, notice there's a bunch here that land on this level of this tree. That's possible. So like I say, now when I do worst case analysis, remember, I try to identify these worst case instances. So remember, it's possible that there can be multiple instances that lead me to one of these longest paths. So that's okay. But remember, when we're trying to establish a lower bound, I don't want to make any assumption about what the algorithm is exactly under only very specific constraints, like our model over here. So I'm going to now try to use this idea to get us a very neat result. And I'm going to try to go back into the recesses of everybody's minds to see if we can connect properties of trees, like our decision tree here, to prove that bound. And believe it or not, it's oddly, like at first you're looking at something like, okay, well, how do I know the height of that tree? Or for any one tree, might I say, any one tree has one of these, it corresponds to a comparison-based sorting algorithm. So how do we use all this? So I'm going to show you, and we're going to walk through this. So I'm going to switch my marker. This one's starting to get a little funky. Let me just, there we go. It's gone. It's gone, everybody. Give rest in peace for the marker. Okay. I'm going to give you a theorem. So here's a theorem. For the sorting problem, I'm supposed to say the. Let me fix that. It's kind of melting there. For the sorting problem, on an array L of n distinct elements, any comparison-based and when I say this, I'm talking about deterministic comparison-based sorting algorithm, but I'll make a remark about that after I finish this. Any comparison-based sorting algorithm must perform big omega n log n. I'll just I'll throw the base 2 in there, just for fun. Comparisons in the worst case. That's what we're going to prove. We're actually going to establish an even better lower bound than we had last time. Last time we had that linear time lower bound of big omega n. That wasn't good enough for me. We need something a little better. And we know that all of those algorithms like merge sort, heap sort, they all fit within the works of a comparison-based sorting algorithm. And this applies to that, which would imply something quite nice, right? That means that for any comparison-based sorting algorithm, if I just assume the elements are just like arbitrary like that, like I have in my model, remember I make very few assumptions, that if you give me a big theta n log n time sorting algorithm, in that case, it's going to be the best possible you're going to do. That's what I'm just telling you. Isn't it kind of neat? So I'm going to give you a proof. And you're going to be very shocked to see how simple this is. That's why I'll tell you that this is one of those things that you'll just remember as just something that'll be in the recesses of your mind. So watch this. So consider any, and I'll just mention deterministic just for the sake of humility, because I sound like I'm just mad with power at this stage. So, and consider any deterministic comparison-based sorting algorithm A. I'm going to call it A. Observe that in the decision tree for A. Now, I have a question for you. For those that are, yeah, exactly, mad with mathematical power. That's exactly it. So I want you to go back to your mind about counting. Okay, if I want to permutate, I want to know the number of permutations of n distinct elements. How many is that? So I'll start writing and you tell me. You tell me. The number of permutations. So if I give you n elements, how many permutations are there of n elements that are all distinct? N factorial. That's factorial. Perfect. See, like I said, you guys are pros. Permutation, the number of permutations of L is n factorial. But what is this? This is the number of leaves in our decision tree, right? All those boxes I had, right? So remember, those are all the permutations of the elements, right? But there's n factorial of those. So just observe. So which is the number of leaves like as in leaf nodes, in the decision tree, right? So now this is where I want you to think back to something you could think about when it comes to so-called binary trees. Now, I want you to think about this. What's the maximum number of leaves you can have in a tree with height h? Just think about that, and I'm going to start writing. Observe that the decision tree is binary. Means it has at most 2 children. So and a binary tree with height h has at most, now I want you to just go back, just think about this. If not, we can derive it right now. So if I have a binary tree, okay, I can have at most 2 children. So imagine you start at the root. You split off. You have 2 like this. So how many nodes did I have in the first level? 1, then 2. Each one of those is going to split, and I'm going to have a split on the other side. 4, 8, and so on. If you actually if you look at the bottommost level of one of these trees, which is the worst possible scenario you're going to have, where you have the maximum number of leaves, they might be all in the bottom row. So if the height is h, that means exactly in the chat, this 2 to the power of h is a bound on the number of leaves that binary tree can have. Perfect. Has at most 2 to the power of h leaves. Bam. Is that nice? So now this is where it gets fun. So at first you might say, Dan, why the heck are you bounding the leaves like this? Well, what I'm going to do is I'm going to use logarithms to kind of effectively bound the height in a special way. So watch this. We're going to use this trick in the future, but I'll just show you here. So the maximum number of comparisons, made by A is the height of its decision tree. Height h. So I'm just going to remind you that's h. And now I'm going to do some little bit of some fun algebra. Watch this. And 2 to the power of h is, of course, a bound on the number of leaves. But how many leaves do I have? I have n factorial of them, right? So we have this relationship we can get right for free from those 2 points I have directly above. Does everybody see that? So the number of leaves is n factorial. And because of this bound, I can relate them in this way. So now I'm just going to do some fun trickery with logarithms. So watch this. I'm going to apply logarithms to both sides of my inequality. So this is true if and only if that I have log base 2 of 2 to the power of h is greater or equal to log base 2 of n factorial. Now, if you remember your properties of logarithms, I have an exponent sitting inside of that log base 2 on the left-hand side. So all I do is I can use the power rule of logarithms to drag that h out front. And log base 2 of 2 is what? Somebody just say it for me. So I have h times log base 2 of 2, which is what? It's 1. Perfect. Thank you, everybody. This is 1. And so now I have, which of course, this all, when I'm done, so I'm using just an implies arrow like this, just because I like to be fancy-pantsy. H is going to be at least log base 2 of n factorial. So if I want to have, so this is actually a bound, so I'm going to have to do at least log base 2 of n factorial number of comparisons in my model. But here's the neat thing. Now I'm going to put this in the notes, just because for the sake of time, I'm not going to go through the full analysis of this at this stage, but it's going to be in the notes if you really just want to see it. This right here is in fact, this is indeed big omega of n log base 2 of n. And effectively that's the proof. End of proof. Yes, yes. So in the worst case, what you could say is the height of that tree is going to be at least log base 2 of n factorial. Yeah, so because remember, this is saying that h is greater than or equal to this. So we're developing a nice, so explain the last part again. Sure. So when I'm doing this, I'm trying to derive a relationship between h and n. So what I did is I used these two facts, these two observations about the decision tree to derive this inequality right here. Now remember, I'm just saying, because remember, I look at all the leaves, and all I'm going to do is I use a property of binary trees, and I can do the following. I can write this like this, because the number of leaves is no more than 2 to the power of h. But I tell you that the number of leaves are n factorial, so this serves as an upper bound. However, when I use logarithms, the whole slick trick here is that when I use logarithms, what ends up happening is the h gets dragged out here, and I end up actually with a lower bound on h. So when I do this, I apply logarithms to both sides, and I do some simplifications. And then what happens is I end up with so notice log base 2 of 2 is just 1. So I just end up with h is greater than or equal to log base 2 of n factorial. And you can prove that this is big omega of n log base 2 of n. Is that good to everybody? So I'll have it in the notes how you derive this and prove this. So if you're wondering, Dan, how did you do that? It's going to be in the notes. So if you're just morbidly curious, you want to find out how to do this, there's a couple ways to do it. I give a nice elementary way of doing it. So just be aware of that. Another way that some people like to derive this result is using so-called Stirling's approximation. I'm not going to talk about that here at this stage, but if you're curious about it, you can always check and look into that. But I generally like to use this nice elementary approach. So are we all good with this? So like I told you, this is deceptively simple, right? Like it's really nice and slick. So notice that, what's the last symbol before h is greater than or equal to? Oh, it's a little clunky, but I'm just saying imply. So it's just a right arrow. So it's just a right arrow. Just like I have if and only if, and I have double arrows like this, if and only if. I'm just using an implies arrow. Yes. So that being said, I'm going to talk, with this, I just have a couple of remarks I want to make just about this result. Now, I did mention to you that this applies for deterministic comparison-based sorting algorithms. And I derived that log base 2 of n factorial for you. So let me just think about this for one moment. Let me think here. One thing I also do have to make a quick remark about is that when you're actually doing this integer based, notice that I made a few assumptions about the power here when I did this. Actually, don't worry too much about it. I have it in the notes. So when I do this, you might ask, okay, well, what about if it's a randomized algorithm? Notice that I talked about previously about quicksort, how you can have a randomized pivot, and that allows me to get the big theta n log n, but with expected running time, meaning it's on expectation or on average, you get the n log n result. You can modify this argument a little further. It's not the exact same, but it's quite similar. And you can derive that the number of comparisons you're going to need is, I think it's the floor of log base 2 of n factorial. I'm just trying to remember this off the top of my head. But this lower bound also applies for average case as well. So if you're wondering about, okay, worst case, average case, and this randomized case, all of them have this n log n lower bound. So, which naturally fits with everything that we've talked about the other day, right? So if you're wondering, oh, can I do in the average case better than n log n for any comparison-based sorting algorithm? The answer is no. The answer is no. This lower bound does actually apply. So it's worth noting, just as a technical note, if you get really picky about some things I've done here, if you want to make sure that log base 2 n and factorial is integer, I would recommend rounding this up if you're talking about this once you apply the logarithm, but that's more of a technical remark. So that being said, I want to make one other note. Is that okay with everybody? I'm just going to make one quick remark, and then we're going to move on to our next topic. Let me just do it over here. So you might ask, Dan, you told me that there's this n log n lower bound. So what happens if is that like universal? Like, is that true for any sorting algorithm? Like any, like period? The answer is no. The answer is no. It only applies to algorithms that apply to that comparison-based sorting algorithm. The comparison-based model. Sorry, I'm getting really ahead of myself. So I want to just stress that lower bounds aren't just about telling you that something's not possible. It's also an invitation. I need to always say this because oftentimes when you talk about topics like this, some just like to say, oh, well, that's it. That's the end of the story. It's actually very often the start of the story, because in computer science, when we find a limitation like this, it gives us an option to explore further. So I just want to make remarks about that for sorting. So before, in my comparison-based sorting model, right, I had it where I just simply said, okay, well, I'm going to make no assumptions about the elements other than they're comparable. Very often in real-world scenarios, that isn't actually going to be something that you'll think like, oh, that's going to be happening all the time. It's going to happen very often, but a lot of the time when we sort stuff, there's often a type associated with that data you're sorting, right? It isn't just like any arbitrary element that's comparable. It's actually something a little bit more specific. So I'm just going to give you an example. So I want you just to try assuming, I just want you to try to assume that each xi, as I had before in L, is either a 1 or a 2. So if you're either a 1 or a 2 in my array, so imagine you have an array. It just consists of 1s and 2s. Can somebody tell me a way I can sort that algorithm better than n log n? So I'll let you think about it, but I'm just going to draw a picture while you think about that. So imagine I just have like 1, 2, 1, 1, 2 like this. So I'm going to give you a brief idea. So have you thought at all about like what I could do to do this a little bit better? Yeah, we count the number of 1s and 2s. Perfect, perfect. That's exactly what I was thinking about trying to do here. So you count the 1s and 2s. In fact, it's sufficient just to count the 1s, for example. So if I just go, okay, well, so if I were to scan this from left to right, and I just count up like a bucket almost, I count up each one. So I have 1, 2, 3. So I have 3 1s. So all I have to do is I set aside 3 elements at the first part, and I say, okay, well, these are all my 1s. 1, 1, 1. And then I can just put the 2s right here, right? And this, of course, runs in Big Theta n. So notice that, and keep in mind, this is like, isn't this beautiful and simple, right? So I'm just trying to give you a warning that just don't look at lower bounds just like it's just the end of the story. It also can be the beginning. So always carefully think about the problem you're studying. So if you aren't looking at that much more broader model, you can do things like this. Another example is that there actually do exist linear time sorting algorithms when the input consists of integers of fixed size. So let me just give you a rough idea what I mean by that. There are so-called non-comparison based sorting algorithms that do exist. Just as an example, for example, if the xi's are all integers, and there's different scenarios for which you could do things with these integers, but I'll just simply mention that for a fixed number of bits. So if you fix the size of these numbers to be like, I don't know, like 8 bits each, what you could do is that there do exist big theta n worst case running time sorting algorithms. Actually, this should be a capital F. Let's put a period on that. Do exist. Just as a remark, for example, you may or may not have ever heard of a thing called radix sort. Radix sort can achieve this under that scenario. So I just mostly want to mention these things. So if you ever find yourself in the future, be like, hey, look, like if I have integers that I'm sorting, are there other alternatives that do exist? And the answer is, of course, yes. So I just want to remark that. So and you might ask, Dan, what the heck is a non-comparison sorting algorithm? Oftentimes what you do is you'd take the assumption like, oh, there's a fixed number of bits, and you'd read off the bits and use them to categorize or bucket the elements in the array into different slots or categories. And then what you could do is each one you read off each bit, for example, and it tells you the quantities of them. And then as you do this, you can kind of selectively refine your buckets down till you get them all sorted. So that's the way, for example, something like radix sort will work. But one thing I do have to point out, yeah, it says radix, sorry. But yeah, no, the big thing I want to just point out is that this is an invitation to study more problems, right? So don't look at the lower bounds like, oh, that's just the end of the story. Just for example, like when we talked about the search problem. What if, for example, you know that the key is always sitting in the first element? Then you know, okay, well, I just pluck off the first element. There may be cases where you have actually a probability distribution. You ask, okay, where is the key in here? And you may be told, oh yeah, no, it's in the first half somewhere. That might give you more information. So there do exist probabilistic versions of a lot of these algorithms. Like I said, they're always an invitation to study unless you truly run into the worst of the worst when it comes to impossibility results, which also do exist. Like some of the examples I've given here are pretty darn like, boom. But what does it mean to be theta n? So I like to say it like this. It makes it a little easier, I find, for students to remember it. Is that if I say big O, I usually like to say like, oh, it's at most. I like to think of this like at most. Big theta, I like to think of it at least. And you just at most asymptotically, at least asymptotically. So big theta is when you have both big O and big omega. So it means it's asymptotically tight. So what I'm saying is that if you were to analyze the algorithm I just described to you in words here, that means that if I did what I do and what you're doing on your work, I could prove that it's big theta n. Is that good, everybody? So that's all I have to say about this. I'm just going to make some remarks, and then we'll talk more about it next class. But I want to talk briefly about so-called amortized analysis. So I just want to kind of prime you for next class. So are we all excited about that? So give me a thumbs up. I want to see some thumbs up. Awesome. Okay, good. So I feed on your thumbs up. They keep me going, like the Energizer Bunny or something. Okay, so perfect. I'm getting my thumbs up. Awesome. So the next thing we're going to talk about is so-called amortized analysis. So I'm going to give you an introduction to this topic because when you study data structures, very often this topic will creep up. And I mean in the nicest of ways. Not like, oh my, it's coming up from the corner, it's going to jump me. No, it's not going to do that. It's one of these things that, so I just want to, so oftentimes, worst case analysis may not capture a more realistic scenario where faster, or what we call inexpensive, operations occur very often, but cannot be effectively represented in the overall worst case. So let me just give you a quick couple examples and then we'll stop for today. So what I'm meaning is that worst case analysis, when we study data structures, say for example you've studied a variety of different ones before, you obviously look for the time it takes for the whole operation to occur, right, in the worst case. Now, the operation in relation to a data structure may actually not necessarily translate to exactly that worst case scenario every single time. The worst case analysis ends up actually being very pessimistic in terms of how you do the analysis. So let me just give you a couple quick examples and we'll stop here. So if I were to give you the insertion or put, whatever you'd like to call it, operation of an array-based dictionary. If you never heard of the word dictionary, just think map or hash map. Or if you don't like that example, or the push operation of an array-based stack. An array-based stack. That's one example. The other one is just hash tables. So you may, in 210, you may have seen hash tables. When we rehash the whole table. So let me just briefly say something about these two examples. So in worst case analysis, when you perform insertions or put operations into an array that's supposed to be some dictionary, but this is also going to be quite applicable to the case where you have an array-based stack. So when you have a stack, for example, and it's just representing as an array, you do a push operation, it puts it into an element in the array, right? And then you do a push, it fills it up, right? As you do more pushes. But what happens when it gets full? What happens is you have to allocate more space for your array, right? So that means you're going to have to copy all of the elements out of your original array and put them in the new larger array, right? But those push operations, those are really cheap, right? I could do those all in constant time, right? So that really expensive operation, when the array is full, that actually gets reflected in the worst case analysis, right? So you would say, hey, look, like when the array gets full, that means that that's like the worst case scenario when I have a push operation in an array-based implementation of a stack, right? But in realistic scenarios, you're going to most likely run into cases where you're just going to push it, you're just going to insert it into the array, and that takes constant time, right? So notice how the worst case analysis is incredibly pessimistic when you do this. Likewise, when you have a hash table. In a lot of probing schemes that you use in a hash table, you'll allocate your array of a certain size, or table if you want to think of it like that. and you would hash into your table like your spots, right? Most of the time you're going to get not so many collisions depending on your hashing scheme. However, most of these probing schemes are going to be accompanying and quite nicely going to include the case when the table's full. So what do you do when the table is full in a hash table and you want to put something in it? You're going to have to create a larger array or table, and you're going to have to rehash all of the data from your hash table into this larger one. So when you're doing the hashing though, on average, the insertions are going to probably be very, very cheap, right? But when you have to rehash the whole table, you're going to have to copy all those elements and insert them into this new hash table, right? That's expensive. So in both of these scenarios, worst case analysis doesn't do a very good job of reflecting these cases, right? So we're going to introduce this amortized analysis to try to capture a more realistic scenario for which this occurs. So does everybody understand what we're going to do next time? I think it's pretty neat. It's pretty neat. So this is very natural when you study data structures. That's why I'm going to show it to you. So that being said, I'm going to stop right here. I want to say thank you very much and have yourself a beautiful day. I'll see you later.